Hello, everybody. My name is Wen, and I'm co-presenting with Steven today on SMB3 landscape and directions. The agenda for today has mainly four areas. We have a few newly introduced protocol changes that involves some isolated transport feature and some new RDMA transforms features. And then we will also talk about some new management options given to the encryption and compression options in SMB. And last but not least, we will talk about some recent improvements and bug fixes that we have done in SMB. So the first area we will talk about is isolated transports. So this is a feature we introduced earlier this year. It may not have been released, but here is the design concept. So before this feature, so you can only have one logical connection between the client and server. So any sessions or tree connects must share the same underlying SMB connections. But what if you have certain SMB shares that don't desire a certain subset of connection type? So in this diagram, for example, if you have some shares that don't want to use RDMA for some reason, but if you have some shares that do, so with this feature, you can have a isolated, what's called an isolated transport logical connection. So what happens here is, so you can specify on the server side when you create that share, you say, hey, I don't care what connection is used, so you'll be defaulted to the default logical connection. Or you could say, I want to client to try to use the isolated transport connection. Because I might want, in our scenario, is like I might want to utilize RDMA. And then on the client side, so this is conveyed via the tree connect response, and on the client side, if it sees that flag, it will try to establish that tree connect through that isolated transport. So in this context, so on the client side, we provided a registry key to disable RDMA on the default connection, but the isolated transport can still use RDMA connection. So in this way, you can sort of choose like whether you want to use RDMA or not, for that particular share you created. So this is a new feature, isolated transport. So. And then next we can move on to some RDMA transform features that we added. So this is also a recap from some previous years SDC talk that we shared. Like the RDMA encryption and signing, and so in the future we will also be adding RDMA compression feature in SMB. So these are all included in the RDMA transforms. So this as a recap, so what needs to happen for RDMA transform is, so first, both the client and server have to support this feature. So, and if you're familiar with SMB RDMA, you might understand that like there's SMB encryption and signing supported like even before this feature over RDMA, and but the difference here is that so this feature utilizes direct data placement just as like SMB RDMA using plain text would. But it used to be when you opt in for encryption or signing, it won't be able to use direct data placement. So there was a performance implication there when it used to be. So with this change, with utilizing direct data placement, things, at least from our tests, are getting quite some better results in performance-wise. So so this negotiation capability ensures that the client and the server both supports this new feature. And so if you're familiar with SMB negotiation, so this is just like many other capabilities that you can negotiate in SMB. So here it's so you have a transform count in the struct. You specify how many types of transforms do I support, encryption, signing, compression, or a subset of those, right? And then you have like an array of the IDs, transform IDs that you support. So and then like server so client sends what it supports, right? And then server responds with a subset of that what the server supports and want to use, right? So there's a new packet design for or packet payload design for read and write over transformed RDMA. So so if you're familiar with the plain text RDMA, right? So there's a there's a token you have to obtain in order to use direct data placement from the RNIC, and then you send the token to the other side, and then it can pull or push the data. So in this case, let's use SMB to write as an example. So once you so your token here we call it RDMA descriptor, which used to be the only thing in the payload, now is a part of the payload, as you can see on the second row on the rightmost part. So what's added here is because transforms usually come with the metadata that's needed to be conveyed to the other side, right? For encryption and signing, that means signature and nonce. So that needs to be included, and then so those will go where you see the transform descriptor list. So it will be a list of descriptors. So why is there a list? Because you might want to interop these transforms that you want to compress before you encrypt, right? Or compress before you sign. Those will be in the future, those will be valid interop. So, there may be even more, like, right, in the even, further in the future. So we support a list of like all these transforms you want to apply to the same buffer, you can have them here, right? So, and then the leftmost on the second row is the header of the RDMA transform, so which we will show right here. So think of it as like on the left side, the RDMA transform is like a header, and then you have a list of different transforms that follow that, and then the end, it's that token that you obtain from the RNIC, right? So let's start with the left here. So you have RDMA transform. So the first two fields here describes the offset and length of that RDMA descriptor, which is the token. So that exists at the end of everything here, right? So so there's just keep in mind of that. And then the channel, if you're familiar, in the plain text RDMA, you have channel V1 or V1 with the remote invalidation. So, but in the plain text one, that channel is in the write request, right? But here we move that to this transform metadata. And then, so in the write request, that channel field will just be called RDMA Transform. So it's a special channel that nests, this actual channel that the RNIC uses, right? So yeah, so just a little bit design concept there. And then the transform count is like how many transforms you applied to the buffer. So if you compress then encrypted, that will be 2, for example, and then 2 reserved fields for future expansion, and as well as 8-byte alignment. So, and then on the right side, so this is just an example of, we're using crypto, so basically encryption or signing as an example of something you can have in the list. So with each list element, the first field needs to be transform type to identify like what transform this is, and then the rest is pertaining to the transform. So in this case, as we were discussing, we have signature and nonce, and we have a reserved just for alignment. And then in this case, what's interesting is like we made the signature and nonce variable sized. So if we introduce new algorithms, things will be very adaptable. So, something to keep in mind here is so if you look on the left, so the RDMA transform, this struct is 8-byte aligned, as we mentioned. So the first person, so the first element in the list, right, will be naturally 8-byte aligned. But the reason we have a padding in the end here at the RDMA crypto transform is we want every subsequent element in the list to also be 8-byte aligned, and also including the RDMA descriptor. So everything 8-byte aligned, right? So so this padding is there to ensure that alignment. So just to talk a little bit about the performance that we collected here. So so this is with a 50 Gbps bandwidth. I believe it's 2 RNICs, so collectively 50 Gbps bandwidth. So both client and server utilizes 4-core CPU to perform the send and receive here. So in the so there's 2 groups, and each group has 5 bars. So the red bar is encryption performance before this change, so without direct data placement. And this should be compared to the green bar, which is encryption with DDP, right? So, and the yellow bar is signing without signing over RDMA without DDP. Light blue bar is signing over RDMA with DDP. And then last but not least, like dark blue as a reference, as a plain text performance reference, right? So as you can see on the left, so on the left it's the write performance, and then on the left is the write performance. On the right side it's the read performance, right? So as you can see, like there's some pretty good perf improvement by using with this feature, by using DDP with the transforms. So encryption roughly had a 2x improvement, right? So did signing, roughly 2x. But if you see the read performance, it's maybe around only 50% better performance. So that is because there is a pending perf work item that we've been working on that had to do with optimizing some buffering when receiving read RDMA transformed read data. So I'll hand it over to Stephen to start with some new management options we've added recently.
Thanks, Juan. Yeah, so let's take a look at the first option of encryption ciphers. So in prior Windows builds with support for SMB encryption, changing the encryption cipher order list was quite tedious and it wasn't very user-friendly. So to change this list, we would need to navigate to the LANman workstation or LANman server paths in the group policy editor, and then we can make the changes there. But for each time we want these changes to take into effect, we would have to unfortunately reboot every time we do this. So it's quite time consuming. The purpose of introducing the PowerShell commandlets for our users is to provide flexibility in terms of usage, depending on things such as performance and security preferences. So for example, if we prefer performance over security, we could prefer the 128-bit encryption algorithms over the 256-bit counterparts. And on the other hand, if we want to prefer security over performance, we could instead prefer the 256-bit versions over their 128-bit counterparts. And also an important note here is that we can prioritize AES GCM over AES CCM for performance reasons as well. So while implementing these new commandlets, we had to consider two key areas where race conditions might occur. So taking a look at the first one, the first area is about the negotiate scenario in the SMB protocol packet exchange process. So a race condition can occur here because the encryption cipher order on the SMB client can change between the time the SMB client sends a negotiate request and the SMB server sends back the negotiate response. So to resolve this issue, we can make something like a snapshot copy of the encryption cipher list that would be used throughout each negotiate request. And it's important to note that the SMB client can send multiple negotiate requests in parallel to different servers. So it's quite possible each request can have a different encryption cipher order. Between each request, the cipher list can change. And lastly, the second area is about how there could be multiple client instances and multiple server instances modifying their own respective encryption cipher list. And to prevent the race conditions from happening here, we can use the reader-writer lock concepts to ensure that there can only be multiple readers when there are no writers and only one writer at a time if there are no readers. And by doing this sort of strategy, we can ensure that we don't reach certain inconsistent states with our cipher lists, which are each present on the SMB client and SMB server. And now I'm going to let Wen talk about the compression opt-in option.
Thanks, Stephen. So we've recently also added a few compression management options. So on the server side, you can now, so when you create a new share, you can now say, I want to request the client, whoever connects to this share, to try and compress data if they support it and the data is compressible, right? So, and that's the first line, the new SMB share compress data command. And then you can also now disable compression by setting on the SMB server configuration, disable compression to true. And this will prevent any outgoing traffic to be compressed on the server. So on the client, we also added a few options for per mapping compression control. So if you prefer PowerShell, you can use new SMB mapping. And if you prefer NetUse, there's also an option for you to opt in for that particular mapping. So something to note here is, for the SMB server, the new SMB share option communicates that it requests the client to compress the data to the share via the tree connect response flag. So there's also some changes in compressibility sampling. So the old default behavior is that we always sample 512 megabytes and then ensure a certain portion of that was saved from the wire before we call that particular FCB compressible. So sampling is per file control block FCB. So now, after collecting feedbacks, we decided to change this to always compress policy by default. And for those who really want the compressibility sampling feature, they can always opt in from the registry to specify the bytes that will be sampled, for example, 512 megabytes or 1 gig, 2 gig, so on and so forth. And then there's also a threshold, which means like how many bytes do I have to save from the wire during the sampling period before I can call this file compressible. So, well, and obviously if it doesn't reach that threshold, compression will be turned off in order to save CPU. So there's flexibility there for people who want that feature. And then I'll hand it back to Stephen to talk about some improvements and bug fixes that we've done over the recent times.
Awesome, great. Yeah, let's start off with the RDS Autodisconnect Timeout. So to begin, what is RDS? RDS stands for the Remote Desktop Services, which allows a server to host multiple and simultaneous client sessions. What RDS provides to its users is mainly the ability to access a virtual desktop and applications remotely or on the cloud without having to have the users install these sort of services or applications on their direct devices. The Autodisconnect Timeout is a marker on the SMB server, and this is used to periodically clean up SMB sessions that have had no open files for the past n minutes. So in the default case, we would have the Autodisconnect Timeout be 15 minutes. So if we head out to the next slide, we can see the overall issue. So we have multiple users who are sharing a single set of connections to a single SMB server with encryption enabled. And this SMB server is hosting a share with files belonging to various users. And here, let's say like this red client on that diagram there, let's say at least one user has a mapped drive to the server without any open files for the past like 15 minutes, which is the Autodisconnect Timeout. So once the user accesses something after idling for those 15 minutes, all of these client sessions get destroyed as an unintended result. So why is this happening? So this is happening because the SMB server does not quite remember the specific SMB session after the 15 minutes has gone, and we have found an SMB session has idled, and this is to optimally allocate resources on the server's end. If the SMB server does not remember the session, it will not have that necessary session key to decrypt the encrypted messages that are currently being sent by an SMB client. And it's important to note that all of the responses the SMB server sends back to the client must include either the message ID or the async ID originally contained in the SMB client's request. And since this cannot be satisfied as well, the SMB client will just wait for 60 seconds until it gets a valid response back from the SMB server with a valid message ID or async ID, because it cannot process just any SMB2 error response without this important information. And once the 60-second timer runs out, the client will disconnect the connection, aka TCP session reset, and this will result in all of these victim clients or the SMB sessions being destroyed. So let's move on to the next slide and take a look at the solutions we discussed. So to improve upon this limitation or unintended result, we recently discussed 4 potential solutions. The first solution is to retain the encryption keys after session destruction. And while this would solve the issue, it would not be a very ideal solution, as it would imply some problems such as security and constraints. For example, a user could idle for any amount of time, let's say hours, days, weeks, or even months before it would re-access the machine again or on the same SMB session. And we would have no idea how long to keep the session keys around before discarding them. And this could also potentially pose as a security issue as well. And the second solution is to not do any idle session disconnects at all when the connection is shared between multiple sessions. And this would work as well, but it is similar to the first solution in that it would not be ideal for optimally allocating resources for the SMB server, because there can be thousands or tens of thousands of idle sessions just sitting around, and we could potentially clean them up. So the third solution, which is potentially a protocol change, is to include the message ID within the SMB transform header. And this also solves the issue for the SMB server response not containing the message ID for the client, for the SMB client to process the error. But this is still not ideal because this involves a lot of backwards compatibility and engineering costs. Also, we have an unanswered question, which is, do we send a plain text message with this solution, or how do we encrypt this message back and send it to the client if we no longer have the session key? And the final solution we discussed, which is also a potential protocol change, it would be to send a notification from the SMB server to the SMB client, similar to how we send a not block break notification. But with this strategy, we would send this notification to disconnect the server entry on the client, and this would seem the most ideal. So let's take a look at this particular solution in the next slide. So here we have the diagram, and for a disclaimer, this solution is still being tested and is currently in development. But in theory, it should mitigate the issue once we have it completely implemented and tested. So assume this client has idle for 15 minutes and the SMB server has already cleaned up the session on its end. So let's note here that the SMB client will still remember this session. And let's say the SMB client sends the encrypted message to the server, as you can see in step 1. And while the server still does not know how to decrypt this request, since it no longer has the session key, it will send back the notification to the SMB client, as noted in step 2, to close the session entry and associated virtual net routes on the SMB client. So the next IO that's sent by the same SMB client should trigger a reconnect or a rebind, and we should technically have a new SMB session state, and we shouldn't be referring to an old one, which was previously triggering the TCP session destruction earlier, where all the victim SMB sessions were being destroyed. So now I'm going to hand it over to Wen to talk about the message ID on cancel request issue.
Yeah, thanks, Stephen. So we discovered a bug recently that the server was rejecting the signature of some ESGMAC signed cancel requests, and we found that this was due to the nonce mismatch when we calculate the signature versus when so when the client calculates the signature, what was sent as the nonce to the server and what server used to calculate the signature. What happened was that so when client calculates the signature, we always use the mid of the request that we want to cancel as part of the mid. And if you are familiar with the nonce structure for GMAC, we also have a cancel bit in that nonce, so that so the mid won't be repeated. But in the scenario when a request has gone async, client still uses the mid that of the request that we're about to cancel, and then plus that cancel bit, right, to form the nonce and calculate the signature. But the client will actually send 0 in the message ID field in the cancel request, so which will cause the server to use 0 as part of the nonce, which then there will be obviously a mismatch between the client, the nonce that client used and the nonce that server used. So we changed, so therefore we changed the protocol requirement. So it used to be like, so the mid here, with the mid that the client sent to the server on async cancel, it used to be it's optionally you can send the mid, or you can just put 0 if as well, and that's still valid. But now because of GMAC requires this special nonce structure, that this nonce formation, we now do require implementations to always send mid of the request that it's canceling, even if the request has gone async, to ensure that nonce matches between the client and server calculation. So yeah, so that's an interesting bug we found about this nonce in cancel here. So next I'll hand it back to Stephen to talk about a Livelock issue.
Awesome, great. Thanks, Wen. So yeah, let's talk about our final issue with the Livelock and the memory map section creation scenario with the SMB redirector. So yeah, to start off, what's a Livelock? A Livelock is similar to a deadlock, but the difference is that we have some set of threads or processes which are repeating the same set of instructions indefinitely, and we're not progressing any further. On the other hand, a deadlock involves some set of processes or threads waiting forever for something to happen such that they obtain the necessary resources. The Livelock we discovered recently involves the memory manager and the SMB redirector. For a recap, the memory manager implements virtual memory and provides the core set of services such as memory mapped files. And the SMB redirector implements the client part of the file and print sharing functionality. So we discovered this issue when working with our independent hardware vendors who were experiencing an internal testing program that was pretty much running forever. And this tool or testing tool is used to stress RDMA traffic over SMB. Our vendors need to pass this test for the Windows hardware quality labs for their RDMA NICs. And this allows if they pass, this allows their device drivers to be tested and signed. What this means is that our vendors can claim that their drivers are working great and ready for use on the Windows OS. So before going through step-by-step how this Livelock issue gets reproduced, let's go through a quick overview of memory mapped files. So on the next slide here, we should see this diagram depicting how memory map files works. And the reason for why we have file mapping is we can work quite efficiently with large files such as databases, and we don't have to load it from disk every time, and we don't have to load it entirely into memory each time. Essentially, we can load parts of this file, we can map into physical memory little by little, for example. So we start off with mapping the file on disk to physical memory. And what's created here is something called a file mapping object, and it's also known as a section object as well. And this section object can consist of different areas representing the file called memory sections. And these memory sections can have one or more elements called views. So these views are what processes can use in their virtual memory to, let's say, to perform, for example, random or sequential I/O. It can essentially read and write to this part of the file. And multiple processes can read and write to the same part of the memory map file in a concurrent manner, given that these views were created from the same memory mapped file. And this is where the efficiency comes in, because we know that the file is on disk, but we are working with the contents of the file in memory, which is much faster. So now if we navigate to the issue itself on the next slide, Let's examine step by step how the issue can be reproduced. So we assume that there are two clients and one server machines with an SMB share that is hosted on the server machine. And let's also assume an empty file to work with on the SMB share. We can assume client number one opens the empty file with shared read and write permissions. So at this point, it should have the read write handle RWH oplock for client caching purposes, assuming leasing is enabled. For a quick recap of these oplocks, RWH, the R oplock allows the SMB client to read from its local cache. The W oplock allows the SMB client to write locally without any need to flush the written data back to the SMB server right away or the down-level file system. And finally, the H oplock allows the SMB client to open and close the file multiple times as long as it's with the same file access and sharing mode, and it wouldn't have to always need to notify the SMB server with these operations. So on the next slide, let's just assume the same client sets the end of file. Let's call this end of file 1, as we see in the diagram, to 196.608 bytes. So the next part is that the same client creates the memory map section. Let's call this the first memory map section number 1. And we establish a view with some dirty pages, let's say 16 kibibytes, and we can go to the next part of the slide. So let's head over to our second client machine and then have it open this very same file, and we open it with the same shared read and write permissions. And once this completes, we should expect our first client machine to have its oplock downgraded to just read handle RH. It will no longer have the W oplock at this point. Next, let's just say our second client machine sets the end of file to 0, and we can call this end of file 2, as we see in the red, which is to 0 bytes. And once this is completed, we can expect our first client machine to have its oplock downgraded to none from RH. So at the same time, we can see that the 16 kibibytes of dirty pages we previously saw in the earlier slide gets purged and flushed to the down-level file system that is present on the SMB server, and that view is now empty at the offset of 131.072 bytes to 196.608 bytes. And essentially here we have data corruption occurring at this point, because now the data the client reads from this view is not exactly to be guaranteed to be the same as what the actual file contents on disk are on the SMB server. But let's put our discussion on data corruption aside until we discuss the solution and its implications later in the slides. So once client number 1 creates a secondary memory map section that has a mapping ending between the end of file 2 and the end of file 1, a Livelock occurs here. So why does this occur? If we go to the next slide, we can see why this might occur. And essentially, without going into too many internal details here, the Livelock is happening because of the highlighted condition that is currently being satisfied. And the start of this Livelock begins with the memory manager querying the file size, which will always give us back the NTFS end of file, or end of file 2 in the example earlier, or 0, due to the lack of the read caching oplock on client number 1. And so memory manager will try to extend the file size, since we need to ensure that the file's end of file, the one that memory manager just queried, is at least the length of the incoming memory map section number 2. So clearly we can see that 0 is less than 147.456 bytes, for example. So this condition is true, and we go to the next operation. So memory manager then will issue some sort of a set file size operation to extend the end of file that we see 0 to 147.456 bytes, which is the incoming section size. And When this flow arrives to the SMB redirector, the redirector will detect that the incoming section end of file, 147456, is much less than the redirector end of file, which is 196608 bytes. And with the current existing logic input redirector, we will actually call back into the memory manager to see if the file can be truncated to the section end of file, or truncating 196608 bytes to 147456 bytes. And overall, this operation will fail because the current logic in memory manager determines that the following checks are true. The first check being the user map section exists, and the second check being the new file size, the section size right now, is less than the current file size or the redirector end of file. And because this truncation check fails, which is attributed to the lack of the op locks and the data corruption, henceforth, we issue a failure status code such as status user mapped file, and then we indefinitely retry these set of operations, hence the Livelock that we see here. So if we go to our next slide to take a look at the solution is to patch the redirector end of file, the 196608 bytes earlier, to the incoming memory map section's end of file size. This way, the condition highlighted in the previous slide would no longer be satisfied, as we are now patching the file size to be, for example, 147456 bytes instead of the 196K. And a caveat of this particular solution is that we could face potential data loss scenarios. And if we were going to go back 2 slides, if we had filled up the entire view with dirty pages before creating the memory map section 2, patching the end of file would result in the data loss in a data loss between what the 147456 byte range to the 196608, and everything before that would be not lost. So to prevent the subset of these sort of scenarios from occurring, we decided to flush the data to the down-level file system during the patching process, so that we wouldn't lose all of this important data after the patch file end of file size. Please join us during the Q&A session, and we look forward to speaking with everyone there. Yeah, thank you for your time and for listening to our presentation.